Okay, our next problem is actually an application of Ramsey's theorem to a plane geometry. And this is a well-known theorem of Erdős and Sekeres in 1935. So theorem states as follows. And this is actually one of the early papers having the Ramsey's theorem. So Ramsey also had a paper in 1930, but this is one of the papers that made it popular, that made the Ramsey theory popular among mathematicians. So let MBN is 3, then there exists n such that any set of n points on the plane R2 in general position. So in general position means that no two are in the same, no two are equal, no three are on one line. Okay, that's, yeah, must have m points forming a convex n-gon. So what is convex? So convex 5-gon looks like this, right? So by convex we usually mean that whenever you have 2 points inside, then any straight line segment is also lies inside. So it's non-convex is like something like this. These 5 points are not convex because whenever these 2 points are inside, but the straight line segments connecting them are outside. And this Erdős-Sekeres theorem says that whenever you have many points, then you can find m points, which forms the convex, which becomes a vertices of the convex n-gon. So I will show you several proofs. All of them uses Ramsey theorem. So here's the original proof. I mean, there are, of course, yeah, I'm not so sure whether this is original, but even in the Erdős-Sekeres paper, you can see many interesting proofs. So let's say n to be a Ramsey number of m and 5 and 4. So this means that whenever we have 4 points, we're going to color them. We color a set of 4 points by red if they form a convex 4-gon, and blue otherwise. Now, by the definition of Ramsey numbers, either there are red m points. By red m points, I mean set of m points whose all 4 subsets are red, or there are blue 5 points. But here's a cute lemma. In any 5 points in general position, there are 4 points forming a convex quadrangulation, I mean 4-gon. So why? Let's look at the convex hull of these 5 points. So the convex, consider the convex hull of the 5 points. 1, 2, 3, 4, 5. Maybe 5 points already from a convex 5-gon, or maybe you only have 4 points, or maybe you only have 3 points in the convex hull. If these two cases you already have a convex, you already have a convex 4-gon. But what about the last case? We have 2 points inside. Then think of the line connecting these two. Then this line cut through the two sides, and then you can have a convex 4-gon like this. So because of this lemma, there are no blue 5 points, because in any 5 points on the plane, there is one set of 4 points which is red. Thus, there exists a set of m points whose 4 subsets are all red. And whenever you have a 4 subsets, whenever you have this property, then they form a convex n-gon. Right? Because if not, you have some point inside, right? So think of the convex hull, and there's a point not on the convex, not on the boundary, then this is inside some triangulations, and these 4 points must be blue, but that's not true, right? Any 4 points are red. So that's the first proof. It depends on this short lemma. And the second proof, actually this short lemma is not by Erdős and Sekeres, but it's due to the what was the name? Due to the wife of Sekeres. Yeah, it's due to Asher Klein. So when they were writing this paper, Asher Klein showed them the result that in any 5 points, 4 of them form a convex 4-gon. And later, Asher Klein and Sekeres got married. So that's why this theorem is called the happy ending theorem by Erdős. And the Sekeres became a professor in Australia. So during the World War II, he was working in Shanghai at factories, and then eventually moved to Australia and become a professor. But he did like his university education was about chemistry, chemical engineering, so has no actual background on mathematics, but he already had several papers on mathematics with Erdős, including this one, so he was able to get a position as a math professor. And later he became the president of Australian Mathematical Society and was working on a math Olympiad in Australia, blah blah blah. Yeah, anyway, that was an interesting story. Let me show you the second proof. Second proof is due to what was the name? Johnson in 1986. Now take n to be Ramsey number of m3. So for any 3 points, we're gonna assign red or blue. How do we assign them? First, for 3 points A, B, C, we color red if the triangle ABC contains even number of other points, and blue otherwise. All right. Now by the Ramsey theorem, there are endpoints such that all triples have the same color. If these are not convex, then there are 4 points such that one is contained in the triangle, right? There are 4 points triangle formed by the other 3. So let's say this is A, B, C, D. Now, if you look at this picture, then look at the number of points inside ABC, and number of points inside ABD, number of points inside ACD, and number of points inside BCD. Now, this is obviously the true statement, right? Because number of points here together with that plus 1 point for D, which is equal to number of points inside ABC. But all of them have the same parity, ABC, ABD, ACD, BCD, because they all have the same color. So in modulo 2, this becomes 0 is equal to 1 modulo 2. That's contradiction. All right. Now let me show you another proof. Again, take n to be the number of 3, m, n, and 3. Now put an ordering for these endpoints, these endpoints. We color A, B, C by red if A, B, C. So if you follow the path A, B, C, A is counterclockwise, and by blue otherwise. Okay, now what you do is by Ramsey there are endpoints such that any triple has the same color. So any triple you order have the same color. Now it's easy that you don't have any 4 points like this. Why? Because among these 3 points, let's say this is the minimum I, and now if you look at this, of course it depends on the ordering between these 3. There's no way that all 3 triangles are compatible, right? So they have to look like this, right? So that means I is smallest and J is smaller than, so let me put numbers. Okay, let's say this is A. Okay, let's look at the ordering. So this is 1, then this is smaller than this, right? And this is smaller than that. But then the last triangle, this is the other way around. That's a contradiction, right? If this is the smallest, and if ordering is the other way around, then this is 2 and 3 and 4. And yet then this is the other way around, right? So no triangle can contain another point among these m points. So that means they form a convex n-gon. And this proof was actually due to Tarsi, who was an undergraduate student in Israel, and he figured this proof during the exam. And in the class, the professor covered the proof, but he missed the class. So during the exam, other students knew the solution, but he didn't know. But he came up with this new proof. That story. And here's the conjecture by Erdős and Szekeres in 1935. They conjecture that n is equal to n 2 to the minus 2 plus 1. And if it's true, then this is tight. There are examples of this many points, minus 1, where you cannot find any convex n-gons. And it's known to be true for small values of m. And previously, most of the, like by previous I mean before 2017, all bounds were something like 4 to the n, or slightly less than 4 to the n, maybe 4 to the n divided by something, and some constant factor. But asymptotically, the growth rate was 4 to the n. But then, in 2017, Andrew Sook made a big breakthrough, proved that n is at most 2 to the m plus 6 times m 2/3 log m for large m. And the proof is completely elementary and combinatorial. And if you have time, you can read it. You may learn this from the discrete geometry course at KAIST. Very recently, 2020, Andres Homson at KAIST and Mozarat and Janos Pak and Tardorj had a paper improving this error term. So it's now the best known bound is something like 2 to the m plus constant times square root of m log m. So instead of 2 over 3, now we have a 1/2 in the exponent. That's current best bound. And these bounds are good because the conjecture is asymptotically 2 to the m. Here it's a 2 to the m. Right? So asymptotically, Erdős-Szekeres conjecture is reserved. Of course, we are still far from actually proving the tight bound. All right.